Okay, very good afternoon to you, everyone present here. On behalf of the International Association of Geomorphologists, I welcome you all for this IAG Geomorphology Week that starts today and would continue till 8th March. Myself, Dr. Shantan Das from India, and I am one of the coordinators for this International Association of Geomorphologists webinar for South and West Asia. My fellow coordinators are Professor Hakan Yiğit Basoglu from Turkey, Dr. Nurul Islam from Bangladesh, Dr. Nargis Karimnezad from Iran, and Dr. Kapil Ghosh from India. Now, before starting the proceedings, I would request everyone to observe a minute of silence in memory of those who have lost their lives in the devastating earthquake that occurred recently in Turkey and Syria. Thank you all. As coordinators, it is our honor to introduce the speakers for today's event. But before that, I would like to request the President of the International Association of Geomorphologists, Professor Sunil Kumar De, to give the inaugural speech.
Thank you, Shantan. On behalf of the International Association of Geomorphologists, I welcome all the coordinators, speakers, and the participants on the first day of this International Geomorphology Week webinar. This webinar was decided in 2019 in the IAG Executive Committee meeting, which was held in Greece, Athens. Which was held in September in Athens, Greece. But immediately after that, we planned for this organizing the series of lectures through this webinar in the first week of March. The background of this webinar was that International Association of Geomorphologists could establish its base, legal base. And now we are legally recognized throughout the world, and our headquarters is in Madrid, Spain. After that, we have already organized 3 International Geomorphology Week webinars. About this webinar we are organizing in this year, we are organizing 11 regional webinars. This is the first day and first webinar organized by this International Association of Geomorphology. Apart from this, there will be 10 regional webinars, and all of you can also register freely from Eventbrite website. Along with this webinar, since 8 March is the International Women Day, every year this Hellenic Committee of Geomorphologists proposed to celebrate this day with organizing this international international webinar series as the Women in Geomorphology. So 8 March, I request all of you to log in to that portal also to participate this Women in Geomorphology lecture series. And all of the speakers, organizers will be women on that day. Apart from this, from 2022, we have started to celebrate International Geodiversity Day. we have under this International Association of Geomorphologists, we have a group, those who are working sincerely, and in that group, the leader is Professor Piotr Migon. He is from Poland, and many others are also there. For example, Zibi Jolinski, he is also from Poland, Paolo Croazza from Italy, and many others. This last year, this IUGS, International Union of Geological Sciences, they published one volume on 100 geosites of the world, in which 3 geosites were proposed by this group and it was accepted. We have decided to continue to this working group also. So 6th October, we are celebrating this International Geodiversity Day every year, and from the last year we have started it. Apart from this, International Association of Geomorphologists' main motto is to promote the young geomorphologists. There is a rule of these young geomorphologists, those who have submitted PhD thesis or awarded PhD thesis. After that 7 years time period, they are getting to apply for any type of scholarships. By this time, since 2001, we have almost offered 250 scholarships to young geomorphologists. And many of the young geomorphologists, those who have received this scholarship, now they are in the executive committee of the International Association of Geomorphologists. We have 2 regional conferences in between. This year in September, it is going to be held in Turkey, and next year it will be held in Romania. After that, in 2026, the International Conference of Geomorphology will be held in New Zealand in 2026. So I would request you to all to try to participate all the regional and international conferences. So this is all about the brief of this International Geomorphology Week and the main agenda of the IAG. I'm glad to say that outside Europe, in Europe, there are several young geomorphologists group in different countries. Outside Europe, one is India, another one is Australia. They have framed this active working groups since 2019. Indian Institute of Geomorphologists, young geomorphologists from, they are organizing different intensive training programs very well and sincerely. This year also, they are organizing. From tomorrow, it will be started. I once again thank our Vice President, Professor Takashi Oguchi, and our webmaster and our IAG EC member, Professor Susan Conway, to organize this International Geomorphology Week very sincerely and efficiently. So with this, I am leaving the floor to these speakers to continue this International Geomorphology Week first, this webinar series. Thank you very much, Sayantan, and all the speakers and these participants. Thank you once again.
Good afternoon, everybody. As I had, proposed earlier, that I would like to speak on something which we have been doing as a team from Jawaharlal Nehru University over the years. So we are trying to look at how the glaciers have behaved over time and space, and what we get out of this to understand how the global climate has synchronity or asynchronity. So,
Sir, just sorry to interrupt.
Something which I had shared earlier. So I'm looking at 3 areas, the source areas of 3 rivers, Bias, Chandrabhaga or Chanam, and Ravi. This is where we have been working in past almost 10 years, 15 years, besides Central Himalayas. And what we have ultimately found from the techniques that we use, multiple techniques to determine the ages, optical dating, radiocarbon, and exposure area, that our glaciers have a very different story to tell when it comes to this part of subcontinent. To begin with, this is the area.
Sir, the presentation mode is not on. The slide is stuck.
Not changing.
No, it is not changing here.
Okay.
So maybe you can just stop sharing and then again you can share the screen.
Okay.
We can only see the first slide, that is Antiquity of Local Last Glacial Maximum, the title slide.
Okay. So in full screen mode, you have put. Is this visible now?
No,
This is
sir.
the third slide. It is?
No. Sometimes it happens because of the computer version.
Uh,
So this BC sign is there. Yeah, I can see
Yes.
your mouse, sir. Yes, but this is not the presentation mode. We can see the PowerPoint, but not in the present.
let us
Okay, yes.
let us go ahead with this. Otherwise, we are going to waste time.
Okay,
So this is the area where three major rivers originate from: Chenab, Byas, and Ravi. So we happen to work in the source areas over the years, and what we find is the processes which work post glacial episode is extremely fast, and this results into destroying the evidences of the earlier glaciers. But some of the signs are still there, some of the extents in some pockets. So we try to locate these over this decade and a half, and I have tried different techniques to work out what were the ages, what was the size of the glacier, whether these were, synchronous with the rest of the areas or rest of the continent and regions. So this is something which is necessary. If you look at this arrow, this is the glacier that we have. This is the terminus. This is not a very large glacier. This possibly is about 4 kilometers long. But the details that we have in the front are more or less destroyed by the post-glacial processes of slopes and periglacial processes. So this is very difficult, in fact, to identify which event happened at one point of time. So, but as I said, most of the glacial deposits, previous deposits, have been destroyed in most of these areas. So this area is semi-arid area, and in semi-arid, plus the upper area is semi-arid. The one I'm sharing here is semi-arid area. So these areas have lost quite a bit of landforms of previous glaciers, glaciation. And if you look at in recent years also, whatever the terraces, these terraces are glaciofluvial terraces of one of the largest glaciers of the area, which is longest glaciers of the area, not the largest, but longest, 27 kilometers long. So in the frontal area, the sediments are there, but in recent years, the glaciers are receding fast. So that results into the meltwater, increased meltwater, and the changes that are happening in the discharge. So many of these terraces are threatened now by the erosion. And subsequent to, as I said earlier, subsequent to the glacial maximum of the area, most of the slopes also fail. So slope failure is very common in this area. So the previous landforms which we could have dated to understand when it happened is destroyed, except for very small areas, and I'll share that. And in the upper area where precipitation is less, snowfall also is, liquid precipitation is very less. Solid precipitation is also less. So it has become a semi-arid area, whereas these were the source areas of one of the largest glaciers of this area. And permafrost leads to cross-hatching, and cross-hatching again, if you look at in the center here, leads to destruction of previous signatures of glaciers, whatever we have. Now, some of the glaciers still contain the maximum extent closer to its accumulation area. So these are lateral moraines, the erratic sitting on these lateral moraines. These are the ones which we have picked up to rework what was the extent of the glacier previously. Now, this is one area where three tributaries had glaciers condensing here. So there was a confluence of glaciers here. And if you look at this is the river that goes, this is River Bhaga, the tributary of River Chandra Bhaga combined. So from here onwards, if you look at the trunk valley, the typical glacial trough, this was created by three glaciers coming from three directions and getting into the lower areas. Now, this has resulted into some of the trim lines which are still there. So we worked on the trim lines. We have not dated the trim lines, but we have dated those sediments which we thought are better than the trim lines to pick up. And this was the area where two glaciers came, and one had blocked the stream flow, leading into accumulation of a huge, thick lacustine sediment. So we have dated that. We have tried to date that using optical technique. And in south-facing slopes on Pir Panjal, this is Bias. The terminal that we found of one of the largest extent of the glaciers terminated at Manali at 2,050 meters. And that we got not from the other sediments, but erratics left behind in the area. Now, so these are the left behind deposits, the erratics that we picked up. These are the ones we worked for the maximum extent, the largest extent, and also for optical dating, we located rest of the sites which are lacustine and aeolian deposits in the entire area. So some of the most beautiful features which have been left behind are drumlins in broad areas where glaciers coming from different streams and different valleys were joining at one point of time. So these have broadened the area, leading into leaving behind some of the drumlins, but these drumlins recent within 9,000 years. So this is not that, okay, this is the Holocene extent that we are looking at. Now, some of these erratics are very beautifully marked all over, and we have put the dates also of exposure dates. This is beryllium 10, 39,000. So Bias, the glacier at 39,000 years ago terminated at close to close to a town now known as Manali. If you look at this table, most of this event is much older than what we consider as last glacial maximum world over. But the largest of the extent that we had of the largest of the extent, this is India, which is created by the glacial processes, deposits. So we dated this landform, which comes to about 80,000 years ago. So the largest leftover of the glacier is the largest extent was something like 80,000 years ago for this area. Now, some of the optical ages that we have got, these are fairly old, reaching almost 5 E of isotope space. And what we see is these are the areas. This is feldspar, which we have Suresh has done this work in this area. So 120 to 130 Ka is the timing for this largest of the glaciers. But in the frontal areas, we have 80, as I said, shown earlier. So 130, 110, 132, 21, so large areas. We did some CRN, but CRN dating, the exposure dating is very young. Possibly it's because of the shielding, because of the toppling of the boulders also. So we couldn't make out much of it except for the Holocene expansions. The largest expansion of Chandrabhaga combined terminated at 3,000 meters. So this remnant is still there. So one can go and visit. We have dated it to be around 8,000 years ago. Now, this was the largest of the extent of the glacier. When it was, all the glaciers came together at around 80,000 years ago. Ever since, the glaciers have become smaller and smaller over the time. 80,000 years ago, 9,000, still smaller. In present day, we can see what is really happening with the present day glaciers. Now for Bias, 39,000 to 82,000 is what we say, but then we still need to work on this, whether it's 39,000 years ago that it terminated at Manali, or it has to be verified. We are still working on this. Now, in terms of Rabi, if you look at Rabi terminated, Rabi is again southwest glacier with southwest aspect, or valley with southwest aspect. It also expanded, but then today glaciers are very small. Rabi has less of a record because of the constricted nature of the topography and steep slopes. And in the frontal areas of Dholadhar, we have tried to pick up the erratics. There are plenty, which was first reported in, I think, was it Egerton? 1880s, it was reported that the glacier had expanded. So it's 235 Ka to 115 Ka to 235 Ka. We have some ages which we would like to update for the future. So possibly one of the largest, largest expansion when it went into the Bias Basin of Kangla Valley and terminated at around 900 meters, has to be fairly old. So these ages that we are getting from exposure dating is encouraging. Still, some of the landforms that we have listed here are the only remnants of the last glacial, but we can still pick up more and date it and understand what is really happening. So 80,000 is the timing we are keeping as one of the largest expansions. But we did try to look at the recent migrations called climate-induced migration using radiocarbon, which comes to something like 13th century to middle of 19th century. Post middle of 19th century, people migrated from the higher altitude areas. So we do not understand why they migrated. Is it because it got cooler by shortening their cropping season, which is the only explanation we could find. Thank you very much. I'm open for questions. I thought I will stick to the time schedule, and that is to thank you. Thank you very much.
Thank you very much, sir, and thank you for sticking to the time limit. So maybe we can take one or two very short questions if you have something.
Most welcome.
Yes. Anyone, you can unmute yourself and ask question, or you can type the question in the chat box also. I'll wait here for 1 minute.
Well, no questions? Please feel free, because we expect that your questions will help us to streamline our future investigations and help us to have the reasons for better techniques to be used. So if you have any questions, please do feel free.
Before starting my presentation, I would like to express my deep sorrow and condolences for the victims of the earthquake that hit Turkey and Syria on the 6th of February. And this is very sad and devastating event. And it's also sad today to present this earthquake-induced landslides. It's also, we are still working on, and starting from this weekend, we will be in field work for mapping and understand the landslide effects on different critical infrastructures. So today, I'm going to present the landslides as a natural seismometer, how they important to record the earthquake rupture sequence and dynamics in different tectonic and climatic regions. And I'm a geomorphologist. I did my PhD on different earthquake-induced landslides in different sections of the world. And as you can remember, this is a complex interaction between the topography itself and also the mass vesting, especially here on today's topic is the landslides. There is a certain dynamic interaction between the tectonic climate and their feedbacks to erosion. So this is today how this tectonic and earthquake, we call it in a short-term effect of this type of events will also affect the erosion, and that can also further change, also affect the climate and also the sediment blocks, and create some certain sediment problems as well in mountain sections. So the landslides this is a kind of summary from Professor Oliver Kohr from Potsdam. And this is a landslide play a profound role in shaping the Earth's surface, given the sufficient size of the frequency of landslides. Actually, they can help to limit bedrock topographies and so trigger shallow crustal response and even cause some tsunamis for farm fields and soil production, and pose significant hazard to human lives and housing infrastructure and land use in many different parts of the world. So the earthquake is one of the major triggering factors. As you may know, the anthropogenic factors together with the hydrometeorological conditions, the seismicity can trigger a lot of landslides. There are several examples in the world, like Bandyopadhyay earthquake itself triggered more than 200,000 landslides in one sequence, one event. So here we also try to understand. This is a nice summary from Sharma, a paper on JJR Geophysical Review article in 2019. And this is showed that is after the landslides, the earthquakes, and then they triggered certain landslides can create a kind of hazard chain in mountain systems. So they turn and evaluate itself and long lasting in more than 10 years, sometimes 20 years, a lot of problems and the secondary problems, because after such large earthquakes, they change the thresholds on the hill slopes. So what we know from the previous works, we know this large earthquakes above the 6.5 may trigger thousands of landslides in mountain terrains, and in 1970s, especially the Kiefer, and later on there are different researchers like Harp and Gibson, Sasa, and the others. add more information to magnitude and area affected by the landslide relations itself. And they mentioned that distance to epicenter and distance to fault play important role. And another contribution from Malamut, the landslide area frequency size distribution is in different earthquakes, and they are giving the similar areal relationship and the probability density functions, but it changed to considering the magnitude of the events, the magnitude of the earthquakes. This is also a contribution from the Oliver Korup and Yuichi Hayakawa and myself. We present also especially the climate change and also the earthquake-induced landslides, how they record in this power law functions. And you can see the total volume estimation and earthquake moment magnitude. They have certain relations actually. But if you look in the right panel, you can see that there are some frequency size distribution not directly controlled by the magnitude itself. So if you look this Denali earthquake and for instance for the Wenchuan earthquake, the magnitude is quite similar, but the number of the landslides and the frequency area curves is completely different. So filling the research gaps, actually during my PhD thesis, I focused on the different faulting mechanism. Then I said, okay, this is not all events can create the certain amount of landslides in terms of the frequency and size distribution, because the rupturing mechanism itself and the faulting type of the earthquakes is completely different. So you can see the normal faults and thrust faults and the strike slip faults and reverse fault, compressional faults. There is tectonic effect also during the earthquake itself, and also the blind ruptures and the surface ruptures or rupture dynamics propagation from unilateral to bilateral, it differs. For instance, if you count the epicenter from some certain distance to epicenter with a unilateral, it doesn't make sense. But for bilateral, it makes sense, actually, because you put a lot of buffer around the epicenter and then you get to that information. But if you count the unilateral, there is no directivity, for instance, in this site. So then if you create some certain buffers, actually you cannot directly reach, because the fault rupture itself orient the whole seismic waves. So then another information to give the add, this is the difference in faulting steel and fault geometry influence the rupture dynamics and change faulting steel along the strike during the earthquakes affect changes in rupture speed. You can see what I mean. This is the thrust and reverse normal strike slip faults. The final fault displacement, it differs and is higher in thrust reverse faults and quite less in normal to strike slip faulting events. So then the free surface and the deep angle of the fault itself, it plays a really important role, because for instance, for the deep angle of the fault, you can see the surface projection affect more area on the surface top. Let's say this is the mountain side. But if we count and look the deep angle of the fault, for instance, if we have a strike slip faulting event and it's more, the deep angle is quite vertical, then when we project it to the surface, it creates an effect limited environment based on this numerical simulation of the Gillespie et al. In 2000 and 2008. So then, getting this new information, we focus on the number of the co-seismic landslides. You can see in the thrust faulting earthquakes, normal and the strike slip fault earthquakes, it differs. The number at least it differs. And then we found that thrust, they are capable to trigger more landslides than strike slip and normal faulting events. So then our main objective turned to the dynamics of the faulting, together including the topography and rock type, how differs this distribution in different parts of the world. We took many different earthquakes like Haiti in 2010, Denali, Northridge, Aishan Fjord, Wenchuan, and Yushu and Chichi earthquake sequence, triggered landslides and analyzed them. So then the first step is the mapping. You can see that this is the protocol for that we focus for the mapping, because you have to focus on inventory mapping. And that's why you need a before and after satellite image or the aerial photos to understand this distribution, which one is triggered by definitely by the earthquakes. So the first area is the Wenchuan. The Wenchuan is in the eastern side of Lungbenshan Mountains, and this is a thrust faulting area. And this is the Bechuan and the Wenchuan fault create that earthquake. This is, you can see that this is the part of the escape tectonic that create this environment, this harsh mountain topography here. So the Wenchuan earthquake itself is devastating, because you can see this is the Lokoa trees is nearly 11 meters. Based on the thrust faulting, this is 11 meters. The maximum is here in Bechuan town. This is the uplift rate during the earthquake event. So it creates a lot of landslides in different countries along the fault. And more than 200,000 landslides triggered one single event. This is the Dhorde, the largest one. And it's 300 meters run up the mountainside. That landslide is really, really huge. So that earthquake itself creates a lot of landslide dams in mountainsides, creates a lot of problems, and we mapped them point base at that time, 60,000, and together with the Chongshu, they have really high resolution imageries. They reach more than nearly 200,000 landslides in one earthquake sequence. But when you look at this distribution of and distance to fault, you can see this is the first along the rupture line. So from 19 to 17 kilometers, and they are mostly focused on the hanging wall side. And even in Bechuan town, and the rupture itself is dominantly moved from because there is a tier fault, a boundary fault here in Fuxing, and it turns to the strike slip environment in this the rupture dynamics itself, and it differs the faulting sequence and the type. So then we analyze based on this faulting and rupture mechanism in these areas, and we analyze them. You can see this is the hanging wall effect is quite clear, and the landslide density is mostly focused on the hanging wall. And on the thrust fault section and the strike slip section, you can see the distribution of the landslides exactly differs and directly reflect the topography itself, and the long term also it reflects the topography, and itself also reflects the type of faulting. So another example from the Taiwan Chichi earthquake area, you can see this is the distribution. And again, for the Wenchuan, if we look this horizontal to vertical displacement rate, also collected from different researchers, we think this is the fault offset and the vertical reverse offset and the horizontal offset dynamics, together with the inversion of the co-seismic slip, Shen et al. And this is, you can see after the Bechuan, the fault itself is turned to do another type of faulting events. And based on our findings, actually, you can see this is the changing of the deep angle of the fault along after the Bechuan town. It's more steep. And then after it creates, actually, those are the certain sections. You can see here near the Bechuan and Chinchuan area and the near the Wenchuan area. the first one. You can see this is the co-seismic sleep rate, and the brownish one showing the landslide area size distribution, how those complex rupture mechanism recorded by landslides itself. So this is actually also another example. We have also a publication in Quaternary Science Reviews on that earthquake. Why so few? So this is the same magnitude event in Denali, Alaska, similar to the Ventron, but produced more or less landslides comparing with the Ventron itself. This event only creates around 2,000 landslides. Still, there are some large landslides because the environment changed to a little bit glaciated environments. And based on here, this we found actually the glaciated and non-glaciated, dry or wet areas, also climate has certain roles. And you can see those are some rock avalanches. And because of the starting the earthquake shaking, the landslides triggered by the event and itself, when they touch and they change the friction, and they add more water because the glaciated environment add more water, and they run out size and turn to rock avalanche, and they run out is really, really high. Some of them reach to 12 kilometers, especially in the northern Black Rapid Glacier.
Professor, please kindly wind up a bit faster.
Sorry?
We are lagging behind the schedule slightly, so could you please wind up a bit faster?
Yeah, sure.
Yeah, thank you.
We also recorded this subshear or the supershear of the event. Rupture dynamics can record and differ because the subshear is more slowly than the supershear. So then the directivity and the rupture speed is really important here as well. And I will show you the one example near the Slana River. You can see that most of the landslides focus on exactly the rupture directivity of the similar side slopes as the rupture, the fault rupture moved. So we have also some results pre-earthquake inventory and the post-event earthquake inventories compared in the blind rupture faulting events in Haiti area. We found also if the surface earthquake creates surface rupture, the distribution is completely different than the blind rupture events. So we also suggested these findings in a paper in geomorphology and the Haiti earthquake. We discussed the type of hanging wall, footfall effect, and different faulting mechanism for the geological and geomorphological evidence for different limits for the soil slides and the rock failures itself. So we come up to conceptual model to say that, okay, differing from the magnitude and the type of the faulting and the rupture dynamics, the thrust reverse faults capable to trigger more landslides than the strike slip events. And today also, this is the case in Turkey. We have not that much landslides triggered by this event, around 3,000, I can say now, we mapped already. And this is based on the suggested by the Fan et al, similar with the three-dimensional of our findings. This is the reverse faulting and the strike slip faulting event. This is the hanging wall effect is quite high here, and also affected area is quite larger. And we put all the landslide inventories, co-seismic inventories in an open repository under the USGS. And this is open for everybody, can download and analyze further assessment of those landslides. I think we reach already more than 36 now, seismic inventories. And there are some pictures from the landslides taken by the Turkish earthquake sequence. You can see here. If you have any questions, I'm happy to answer them. Thank you very much.
Good morning, everybody. Now we move on to the Bengal Delta. As you can see here in this diagram, we have shown the Ganga Basin, which drains from the Tibetan highlands to the central India. All these sediments eroded here ends up here at the Ganga, Brahmaputra, Meghna Delta. But the region we are going to focus on, the western part of the Ganga Delta, Ganga, Brahmaputra, Meghna, is basically contributed by the Ganga River only. Now, what you see here in green color are basically the Sundarbans or the mangroves, very well known, one of the World Heritage Sites, the largest extent of continuous mangrove patches in the world. That was the extent in 1779 when this area was first mapped. But from before that, some important development took place in the lower part of this delta. The distributaries that once contributed the western delta decayed one after another. So all these rivers which you can see no longer brings any sediment to the western delta. So that is the reason why it is called the abundant Ganga, Brahmaputra, Meghna delta. Later on the westernmost side, there is some artificial resuscitation of a river, so that brings up some sediments. Now, as you can see here, this is how the mangroves dwindled, that is deforestation occurred with the reclamation, with the coastal reclamation. The present extent of the mangroves shown in green are about 40% what they used to be in 1779. Now, if we just focus on this area, I hope you were able to make out this marker here and enlarge this region. A typical picture of the Sundarban region comes out. As you can see, here you have a non-reclaimed forests, and on the north, you have the reclaimed region. In the forested region, tide comes twice a day, it gets vertically accreted, and lot of sedimentation and erosion that goes on. And on the other hand, on the northern part, it's all reclaimed. Means again, if I again enlarge this region here, you can understand a log gate is there. The water, the high tide on the northern side, southern side, and so water is entering in the north because the tide, the Swiss is raised, and so it's a completely a controlled ecology. So the tides which replenishes the forested region cannot replenish the northern region. It's all controlled. Okay, that brings up with this background, we come up to what has happened in the Sundarban lowlands during the last century. Okay. What you see here is a tide gauge. The tide gauge operated manually or seen manually. This is a low tide. The same tide gauge in the high tide. And so this is the tidal range, what we see. Low tide and the high tide, they make up the tidal range, what you see here. And the mean sea level is determined as the average of these two. And when we think of increase in mean sea level or trend of mean sea level over the years, we need to go on averaging these two extremes for days, for months, for years, for many years. So using that, so this is the mean sea level, using that data from the permanent mean sea level station for mean sea level, PSMSL, gives us this picture of all the tide gauges all around Sundarban. And among these, the most important, what we consider to be the most important station is the Diamond Harbour, which has got almost close to 80 years of continuous recording of sea level, sea levels at the water levels. And that shows that the water level is rising here at 3.84 millimeter per year. And if we consider the other gauges, we find that the tide sea level rise is actually increasing as we go up because of the constricted estuaries, which is the hallmark of macrotidal estuaries. And if you say that the extent of tidal rise, or you might say the range of the rate of rise of the sea level is between 3 to 4 millimeter per year for the entire delta, we won't be very wrong. And we can compare this 3.84 millimeter with the satellite altimetry based data, of the sea level just south of the Sundarban, and it shows it to be around 3.89 millimeter per year, which is not very much different from what we have got from the tidal gauges. Okay, now this shows the typical scenery of the Sundarban region. On the left, you have a estuary or a river, and on the right, you have the reclaimed region. Imagine what would happen if this embankment was not there. This is one of the very few places of the earth where the boat is plying, or they regularly ply during the high tide above the level of the land. And to measure it exactly, this embankment which is separating the water level and from inundating the area to the east, to the right, is basically just 0.5 millimeter high. And now, next slide would show that what would happen if a cyclone takes place right at the moment of the high tide. This is taken from the YouTube, one of the recent cyclones, and you would say there is no water and there is no rain, there is no cloud, but still the water is being overflown out of the, because it is the high tide in the estuaries and the cyclone has struck place right at that time. Okay, so this is prior to a major cyclone. And this image, you can see the reclaimed regions on the north, and this is the after a major cyclone. The entire region is underwater. The reclaimed region is underwater. And that is one solution that will increase the level of the embankments to stop the water to rushing. But there are a lot of problems in that, because once you stop the waters to enter the region, the reclaimed region remains far lower than the forested region where the tidal free flow can occur. Okay, very quickly, if we go through the cyclones that took place or struck this region during 140 years, and if we just pick up this small region here, which forms the northern delta, it's a mess really, but from the mess we can see a pattern. And this shows decade-wise the median position of the storm strikes. And very interestingly, we see this green line here at the Sundarban region, starting from 1961 to 1980. Starting from 1961, all the cyclones that had struck this region has a tendency to concentrate on the Sundarban. And there have been many predictions of what the Sundarban is going to see like in about 30 years from now. That's that time is very close. This is from the very well-known site that predicts these sort of things, the climatecentral.org. And this particular image is from the WWF, the Worldwide Fund for Nature, and it also shows that Sundarban in 2050 may have to be completely abandoned, and the population living here, no less than close to 6 million people, if we include Bangladesh with India, in both of these countries, will have to housed in interior regions in multi-storied houses. But one thing we must also consider with this, that in the pristine Sundarban region, there is a lot of vertical accretion going on. What is that? See, during the low water, the tides channels are all exposed. There are no tides. But during the high water, tides go in, and that accretes sediment on the top of it. We used a digital terrain model from Pandemics, and we saw how this thing is affecting the non-reclaimed Sundarban. For example, in this region, this is a part of the Sundarban. From old topographical maps, we had known that this part was reclaimed in 1920s, this in 1940s, and this in 1980s. And when we superpose the digital terrain model on it, which shows the land level, it shows the land level on the top of it, and it shows that the regions that was reclaimed at the earliest time are the lowest compared to the regions that were reclaimed more recently. And of course, the forested regions, which are shown in all pink, are the highest regions. Okay, these are some of the data we have from different publications or from our own study of the region and how the vertical accretion is going on in this region. And we see that in the forested region, the rate of rise is around 11 millimeter per year, but up to 11 millimeter per year, that beats the mean sea level rise of 3.84 millimeter a year, quite a lot. And in the reclaimed part of the year, when they are open to tidal spill, the rate is very high, something like 180 to even 700 millimeter per year, close to 1 meter. So that brings us to the concept of tidal river management that shows if these reclaimed regions can be open to the tidal spill, then it can raise its level very fast, maybe even faster, not maybe, but definitely faster than the rate of sea level rise. Now, not only this, not only the this thing about the tidal range I had shown, there is another thing, another characteristics of the tide here, that they are asymmetric. That means if you think of the two troughs and the two crests, you would find that the time of the crest to rise is shorter than the limb, the falling limb to fall. That means this time period here is shorter than the time period here when which is approaching the trough. So the tide is rising fast, falling slow. If you take this example from the Hooghly estuary, we find that the tide goes in 5 hours and comes back in 7 hours. A faster landward movement, a slower seaward movement. That means that all the sediments that it carries in, it cannot bring back. And so we have something situation which we call tidal pumping. That means the sediments go in, get deposited, and the return tide can't bring them back. Okay, and not only that, if we start from the sea to the interior, this asymmetry increases as we go north, and also the tidal range, it also increases as we go north. So in the Sundarban, the processes what is operating in the southern part is different from the processes which are operating on the northern part. Okay, let's see very quickly how that reflects, or how the land forms are changing because of this. We are taking 3 examples from the interior areas of Sundarban, and the places are not important. Just remember those are the interior areas. And you see here in the northernmost part, in what we call the Rangabelia region, we have a creek which was 560 meter wide in 2021. Now it has become just 220 meters. And in the 2 other areas, if you just compare diagonally with the upper left diagram and the lower right diagram, you will find a lot of islands have come up, tidal islands have come up. That means there is a lot of sedimentation going on in the interior part. But if you compare that with the exterior part, for example, here you can see an island known by the name of Bulcheri. And if you see the maps of different years, like 2023, 1942, 1916, 69, 2001, 2014, 16, you find that it is eroding. So this particular island, it is eroding almost linearly. So if you extend that line, you would understand when this will become zero, when this will become completely eroded. And this is happening all through the southern part of the island of the Sundarban, be it the forested region or be it like this reclaimed region. So the entire southern part is eroding. Now we wanted to compile that in maps. Before that, I can quickly share with you some of the field photographs of this region. And now we had taken old maps and satellite images and compared how the entire Sundarban region, more than 250 islands, have changed between 1904 and 1967, a range of 53 years, then a subsequent range of 34 years, and then a subsequent range of 14 years. And this is the whole story. I will come show you the trends shortly. But as you can see here, it's very clear. Green is accretion, which is taking place all through the northern part, the northern island, shown in this color, which is ochre. And the erosion is all prominent in the southern islands, which is shown in red, and the southern islands are shown in yellow, and the central islands are shown in gray. Okay, now this is the whole picture. If you take the whole islands, all the central islands, or the southern islands, you can see that this erosion is going place linearly, really. And if you take the northern islands, you see some accretion. The trend is basically accretional. Now, but why these southern islands are getting eroded? We know this Galloway triangle. It shows that very basic thing that if a delta is dominated by the fluvial rivers, then it will grow up, build towards the sea. But on the other, the wave and tides are erosional. And if there is no sediment supply, the delta will erode. And that is exactly happening here. What we have seen, this western delta is all abundant. It's not receiving any sediment. Whatever sediment is artificially coming from the Bhagirathi Hooghly, it also receives some sediments from the eastern plateaus of India. They are probably going away from the system. And whatever sediment is contributed by this, the largest rivers, some of the largest rivers of the world, the Ganga and the Brahmaputra, and the combined flow of the Ganga Brahmaputra, which is Meghna, they are intercepted by a Sambarin canyon, which separates the eastern delta from the western delta. So whatever is coming here, records show that the eastern delta is gradually accreting. There are a lot of records, but our records show the western delta, the coastal part of the western delta eroding, because all the sediments which are being carried by the waves, they are being, and the currents which are directed towards the west are being intercepted by this swatch of no ground submarine canyon. That's a queer occurrence, but this canyon is there and it's influencing the net sedimentation results of this region. But of course, there are fines. Those fines are, of course, carried in suspension, and that may go, go towards the western side of the delta, and that are coming with the tides towards the interior regions, and so vertical accretion is occurring. So while it is laterally, it is eroding, vertically it is accreting. I know I have come to the end of this, but I would just say that the region, it's a very complicated region because you have sediments coming in, erosion going on, reworking going on, sea level is rising. So it's very difficult to make out. If you take only one island, you are bound to get some misleading results. So say, for example, if we take this island, it is gradually getting eroded. But if you see the entire region, if you see the other islands, surrounding islands, you would find that although this island is getting eroded, some other islands are getting accreted, at least in the interior part of the delta. So there is a lot of sediment reworking is going on. So now we can summarize what we have seen. We have seen that the delta is cut off from the sediments supply from the upland, and then the southern delta is eroding because of delta abandonment and the sediment, this interception by the Swatch no ground canyon, and the relative sea level is of course accreting, going higher, but at the same time the land level is going up due to the tidal pumping and also due to the vertical accretion. Okay, so very shortly, this is the picture, today's picture of the Sundarban region viewed in the perspective of the last 100 years. Thank you.
Okay, well, thank you very much. Good afternoon to everybody. Can you hear me? Is it loud and clear?
I think it's all right. Dr. Shanto, can you hear him? Hello.
Yes, this is all right. This is all right.
Yeah, all right.
Okay, then. Can you see the slides?
Yeah. Yeah, it's all right.
Yes.
Okay, then. Thank you very much. Again, just before going to start, I want to give an example regarding our country. just for my education purpose and for some other purposes, I just visited some of the countries all over the world. And whenever I go somewhere, and just if anybody asks me, just where you come from, I'm from Bangladesh. Where Bangladesh is situated? If I say Bangladesh near to India, then they can recognize sometimes. But in past 20 or 25 years, if I say Bangladesh is, just flood prone area, disaster prone area, can you hear about it? They say, oh yes, Bangladesh is flood prone area, disaster prone area, and we know Bangladesh is very much disaster prone area, and like that. So we are living in disaster prone area, and it is my research is very much related to disasters and related issues. And now I am going to talk about, just flood recurrence probability analysis in the Teesta River, Bangladesh. And it is, just one of the major transboundary river in Bangladesh. So let's start. So, just as Bangladesh, as our colleagues, all of the geomorphologists all over the world, they know Bangladesh where it is situated, and we are bounded by the northern part is just the Great Himalayan range, and southern part is V-shaped, or just funnel-shaped Bay of Bengal. That's why we are facing each and every day lots of disasters, notably just floods and cyclones. So floods is number one, just disasters in Bangladesh, and my research, present research is on it, and it is ongoing research. So it is almost completed, but not fully completed. So some of the data are still we are just processing, and we are trying to just finish this research article. However, my research title, as you see, flood recurrence probability analysis in the Teesta River Basin, Bangladesh. Bangladesh is just crisscrossed by more than 700 rivers. And major three rivers all over the world, just Ganges, Brahmaputra, and Meghna, just Basin, three largest rivers crossed through Bangladesh. And just a total discharge we received in Bangladesh, 93% discharge coming from outside Bangladesh, and we are only generating only 7% discharge in our own country. So that's why we are very much affected by just transboundary rivers. And my just present research, one of the transboundary rivers, it is fourth largest transboundary river. It is the Teesta River, and I am just working on it now. Teesta River, just if you see it, enters from Bangladesh, just this point, Dalia point. The river basin here, you see, it is Indian part, and the lower half of the basin, this part is situated in Bangladesh. So, just it is one of the major rivers in Bangladesh, and water sharing is one of the main issues in our country. So we studied mainly just we are getting plenty of water during rainy season, but we are getting less water during summer season. These are the just problems we are facing in our country. During rainy season, we are getting what we are we need. We are getting more than that, and what we need in summer or dry season, we are getting less than that. So we are working on it. And Teesta River, one of the major issue, we have some little bit dispute with our neighboring countries regarding water sharing. So I don't want to just discuss about that. I want to discuss in my part. But to do just detailed research, I had to collect, just some information from Indian part as well. So because majority of the basin situated in Indian part. And to completion of this research, 180 years data, Indian part, just have collected from just rainfall data collected from Indian part, and in Bangladesh part, not too much data are available, just 59 years, some parts 65 years, some parts 9 years, and 31 years data. So little bit just data inconsistency just prevail in this study. However, we tried to solve those data. And what we did, just we tried to identify the flood recurrence probability and just some processes involved on it. First, I want to show you the just how I just tried to find out those outputs of this research. My methodology mainly drainage basin, drainage density related. These just methods I have used and some digital images and some formulas I have used for this study. So first, we have calculated annual rainfall in upstream basin India, and we saw in the 118 years annual rainfall crossed over 5,000 millimeter 18 times in this basin and 6,000 millimeter 15 times. And in last 48 years, 6 times the total annual rainfall is over 6,000 millimeter and 4 times higher than magnitude of floods hits in the Teesta River areas, and 2,650 millimeter rainfall average condition in the West Bengal and Sikkim and Assam and Meghalaya region. These are the Indian part. And in Bangladesh part, rainfall is data is not too much available. However, if you see the figures, just below 3,000 millimeter rainfall received in some parts, Rangpur, one of the districts, Dinajpur, it is also shows less than 2,500 millimeter, and some other parts, just below 3,000. So we are receiving plenty of rainfall outside Bangladesh, as data shown. And then just water level data. We've analyzed water level data as well. In flow of water from India, Teesta River fluctuates a lot. And average water level Dalia point from where it enters Bangladesh, 50 to 52 meters, and just 50.5 meters average, and just decreasing with time, and it is a little bit decreasing tendency. And in another point, Kaunia point, 26 to 29 meters. So where enters in Bangladesh, water level too much higher. And this is the water level data shows, and you see the water level data in Dalia and Kaunia point, and it is a little bit decreasing tendency. There are some reasons I will just tell you later. And these are the water discharge in Bangladesh part. Just average discharge 6,000 cubic meter per second to 8,000 cubic meter per second, and just in 2001. 10,000, more than 10,000 cubic meter per second water has been recorded. Mentioning flooding situation is not found. A little bit inconsistencies there. But in significant flood, what we observed in last 3 decades, in 1998, more than 30,000 cubic meter per second, 1998, 14,521, and 2014, 16,000. More than almost 17,000 cubic meter discharge we have received. So these are the situations in discharge point of view. Water discharge is, just you see some parts of our Bangladesh part. And then recurrence probability, you see just rainfall recurrence probability in Indian part, and then in Bangladesh part, and then just probability in Bangladesh part. And you see from this table in 1994, if we just rank it, just 1974, sorry, the probability was the rank was high, flooded, and it is recurrence interval is 118 years, and 1921 59 years, and 1998 39 years. And then 1988, 23. These are the significant floods or catastrophic floods we observed, and their recurrence intervals are there here shown. And then just elevation of the Teesta Basin. It is also important to find out just water flow. from digital images, we have calculated this. The highest elevation is in the northern part, more than 8,000 meters, and lowest in Bangladesh, only 17 meters. Can you imagine? Just 17 meters. And the upstream basin, just in Indian part, it is more than 140 meters. In our Bangladesh northern part, is little bit higher. However, it is less than 140 meters, and this lower part is almost flat land. And these are the elevation chart, and you see just 70 to 25 meter and total square kilometer, and up to the total area elevation from upper basin to lower basin. And then you see that these are the dam model, and you can compare these just by observing these different color combination. This part Bangladesh enters this part Teesta here, in the upper part here. This area is stated as lower basin, and this part is totally situated in India, and this is higher part as digital elevation model shows. And the drainage pattern, we calculated drainage pattern as well. It is almost a parallel drainage pattern from lower basin, but little bit dendritic pattern in just higher part of the basin. And then stream order we saw, stream order, sixth order, up to sixth order stream we found in this basin area, and from first order to 16th order, and ratio you can see and bifurcation ratio see, and more than 2 if it is, then it can be considered as higher part of the rivers, and less than 2 is almost flat land. And if you see 5th and 6th order in Bangladesh mainly, it is almost flat land compared to higher part of the Indian part. So next drainage density you see, these are the stream length and drainage density. And drainage density is higher in the first order, as always, in this part. And in this part, drainage density is just compared lower. And then slope of the river. This is one of the important factors. And in the higher part, slope of the Indian part, it is almost 40 plus degrees the slope. And in Bangladesh, you see only 0.44 degrees slope. And according to Singh, just number 5 is slope classification. It is higher slope and steep slope we call it, and just flat land, just less than just 1 or 2. Then it is, we call it, according to him, just flat land. And then catchment basin we have divided. This is Indian part and Bangladesh part also. And out of 55 this basin, 55 sub basins, what we are calling here 55 catchments, 44 plus higher upper basin, and 11 situated in the lower basin. Out of 11, 10 catchment sub basins or catchments situated in Bangladesh part. And then just if you see the digital elevation model and a little bit animation, if just a flood situation you see, you can see a little bit from this animation. Just the speed of flood happens in this area due to slope you observing. Okay, these are the situations, this part. And finally, flood zones. Just following those previous data sets, we have identified flood zones in Bangladesh, and these are the flood zones you see just in Bangladesh. District-wise, we have divided Nilphamari, Lalmonirhat inside Bangladesh. Rangpur, Kurigram, and Gaibhanda, and number of unions I have given you, and proportion or percentage-wise, just these are the percentages. Just we have identified as flood zones, and just this is union-wise, the smallest union in Bangladesh. We call it union, the smallest geographical or political boundary union. These are the things, and these are the just according to influence zone or flooding zone, district wise, and these are the union wise. And finally, what I want to say, just these are the things, as I said earlier, we have not finished yet. However, what just for before 90, it was significant impact, but after 90, we have constructed this barrage inside our part to just control flow, and just utilize our water proportionately during summer and or the rainy season and dry season, and that's why. But the objective of that barrage was totally I should say just it has been not worked properly because of just due to upper riparian area. We are receiving water from our neighbor country, and we are not getting proper share, although just we are working on it. Both our governments are working on it. However, just the reality is we are not just getting too much water during dry period, but rainy season we are getting plenty of water, and just due to over sedimentation in the upper riparian area, desertification, deforestation, we are getting lots of plenty of just sediments. That's why our lower basin is just plenty of chores and bars we observed in our part, and due to if just not very much or plenty of water flow coming to Bangladesh, but we are facing just a huge or catastrophic or severe type of floods because of just river basin upliftment due to sedimentation. So these are the problems, and we are facing both problems. We are not getting water from just our neighboring countries, and although we are just established our Teesta barrage to just properly utilize our water, but due to lack of our just water availability and sedimentation, we are facing another problem in agriculture sector, in just livelihood and some other sectors as well. And finally, we are just facing just lots of just our development work happening in those areas. That's why we are facing this type of problems due to this Teesta barrage and Teesta river water issue. So what we just found in this, just so far we found from this study, just if we don't just properly just share our views and just exchange our problems with our neighboring countries, and our just upper riparian countries also, they are facing problems. That's why they are just taking some measures as well, creating dams and barrages as well. But as we are situated in the lower riparians, we are just affecting more than our higher riparians. So still we are working on it, and that's why my just observation and my research output we are sharing with our just counterpart and in our government to show our neighboring country, friendly countries. So these are the situations we are facing, and what we should do just to reduce these problems or reduce these vulnerable situations, we have to do something. So these are the situations so far I have identified, and I am sharing with you. It was short period of time. I got a notice from our counterpart. That's why I could complete totally this research work. So I think just partially I have shared my views, and if you have any queries and comments, you can just ask me if you think. Thank you very much.
Yeah.
First of all, I thank all of you and all organizers of International Association of Geomorphology, and sorry for this problem. I want to talk about Loess geodiversity in some part of Iran with different geodiversity. I mean to talk about geomorphological perspective. This presentation is prepared by my colleagues and me again. And I guess, would you please do next slide? Okay, let me talk about just some minutes about geodiversity. We have different phases of geodiversity, including topography, geomorphology, hydrology, soil, and geology. And I want to focus on geomorphology in Loess deposit. Since I want to talk about landforms and process, especially in soil erosion, I want to give in detail about Loess deposition in north part of Iran, especially in Kholistan province. Next slide, please. Around 20% of the Kholistan province devoted to Loess deposits, and this area is known as Iranian Loess Plateau. And we have different kinds of Loess here, and most of them that has silt soils or silty Loess is located in the northeastern part of Kholistan province with high silt around or more than 50%. As you know, silt fraction is very sensitive to erosion and is very high susceptible to erosion. Loess deposits are very fragile and fertile from different points of view. For this reason, it's highly or densely cultivated by local farmers. And I'm going to talk about Loess deposit in Iranian Loess Plateau. Next, please. As Dr. Nargis said, I'm going to talk about piping erosion, and we have different works in piping erosion in Iranian Loess Plateau. In this slide, you can see different kinds of, in this slide, you can see different forms of piping with different shape, with different size and different morphology in different land uses that we see in field, and we want to talk and focus on 500 hectare. In next slide, please. So we have different landscapes in this area. Sorry, it's not, I think, animation. It should be, is it possible to start with different animation? Is it animation based?
Unfortunately, because it is not the version with my laptop, I think no, it's not.
Okay, no problem, no problem. We have different kinds of landscape here, different position of piping erosion here, different forms of piping, different land uses, and also different shapes. And since I want to focus on process and landforms, I can highly focus on the erosion. We have different piping and piping prone area. Since Loess deposit is highly susceptible to gully erosion, and the first region of gully erosion is originated from piping, we should pay to piping erosion at the first step of development. We have two different theories to look at the piping. With the soil scientist perspective is a treat, but from the perspective of geomorphologists is a time or is an opportunity for evolving the drainage densities in Loess deposit. And I want to focus on, next please, different land uses. Sorry, it's not animation here, but I can talk about that. We use different images from different temporal time, from 1961 to 2022, to focus on aerial photos, Google Earth, two different UAVs from 2018 and 2019 and 2022. We can see in area of interest around 500 hectare, highly intensive land use change with local farmers. And these land use changes induce piping erosion and intensify piping erosion. And we can see next slide. Here again, we have different animation here, but it's not. I think it's a problem with me. But we have an animation here, different figures, different shows, different animation. But let me go to the next. Here, for example, we have different temporal resolution from 1965 to 2016, 2018, 2019, and 2022. We have different temporal activity of piping erosion. That's the main factor controlling or intensifying piping erosion is land use change. And this land use changes, I think it's the most important factor controlling piping erosion. In this case, local farmers and local landowners feel this collapsed pipes or perhaps intensify piping erosion by some rural roads or perhaps some roads between farms. And I think apart from inherent characteristic of loss to erosion, the role of local landowners should be taken into consideration. Next, please. For example, here, we focus on one small point with different time resolution or temporal changes, and we just talking about quantitative geomorphological point of view for geodiversity to monitor the behavior of piping erosion. And you can see a different behavior of piping erosion for different time, but I think we can use better UAV application in next studies. Let's go again, please. Let's continue. Next, please. Here again, another piping activity in different times. You can see from aerial photos to Google Earth, UAV in different times, and Google Earth again, different behavior of piping erosion. And I think apart from external factors controlling piping behavior, we should take into consideration internal behavior of loess deposits, and we paid to loess deposits and deeper soil characteristics. And I think some soil characteristics controlling underground behavior like ESP, like sodium, that it can intensify tunnel erosion. And next slide, please. Here again, another pipe position in different time or different temporal position. You can see just emerging of piping, and it's just in 40 years. We can see and we can detect the piping erosion. And I think geomorphological point of view or geomorpho characteristic or geodiversity is highly important to pay to it. Apart from geology geodiversity, geomorpho diversity is highly important, especially to paying to different kinds of erosion and gully erosion, piping erosion, and some derivatives. Next, please. Next, please continue again. Next slide. Yeah. And if I want to briefly talking about my presentation, from different time, we have different land uses. You can see the rangeland area is decreasing, and in front farmland areas is increasing. So land use changes is clearly important here. The area of interest is nearly 226 to 548 meter, and the mean slope is around 35%. So in this small area, you can see different intensified piping erosion. For example, in 1961, we just had 176 pipes. It increased 324 in 2016, 364 in 2018, and the same number in 2019, and perhaps the same number or 2022 around 365. So just in 4 decades, the number of piping increased or doubled, and it's very important for us to know the behavior of piping erosion, to pay to geodiversity in the same land, in the same formation, in the same soil, in the same quaternary formation, especially Loess, and we see different behavior of piping, different increasing the number, increasing the size, and etc. In this talking, we just focus on quantitative geomorphology point of view for geodiversity, and we have the future working to paying to quantifying geomorphology behavior of geodiversity and paying to underground behavior of piping and tunnel erosion with some field surveying like GPR and PRT, and using some high-tech aerial application or UAV, and some photos or some map pilot to know in detail the behavior of pipe, especially in size, volume, and to detect the behavior of pipes in different seasons, and to know the behavior or role of biodiversity for controlling piping. And the next. Thanks for you that lets me to talk in this international webinar, and thanks Nargis, thanks all co-organizers, and sorry for some interruption in my talking and presentation. If you have any question, I'm ready to talk and answer.
So the talk today, I'm going to talk upon the framing conceptual models for mechanism of sediment bypassing at the tidal inlets along coastal tracts of India. Now, these tidal inlets are the prevalent morphologic features along the coastline, and these are in fact the most dynamic features along the coast. They basically serve as extremely important conduits for exchange of water and sediments between the bays, lagoons, or estuaries and the sea. Tidal inlets on the open ocean coastline often represents a significant sediment sink for littoral cells. They are capable of removing considerable sediment from the longshore drift. However, when we take into consideration natural inlets in equilibrium, they may develop methods that allow a major fraction of the longshore transport to bypass around the inlet to the downdrift beaches. In this connection, inlet sediment bypassing is a process by which sediment moves from the updrift to the downdrift side of the inlet and involves the inlet channel and the ebb-tidal delta. Sediment movement onshore typically takes place in the form of large landward migrating swash bars. Now, these may vary in size. Part of the sediments those move along the downdrift beach may be recirculated back to the inlet, or they can even get further transferred down the Bali. In either case, sediment movement will be totally determined by the morphology of the ebb-tidal delta and the wave approach. These general patterns of the sand transport result in sediment bypassing at the inlet. Saying so, this paper basically attempts at framing mechanisms by which sand is transferred to the downward shoreline at the tidal inlets along the coastal tracts of Maharashtra. After a continuous survey over this region for more than 15 years and some specific regions specifically, working on that, I have come to this formulation of 4 basic models for this region. Now, before we venture into the model, let us have a look at the general setup of this region. Now, this is the coastal tract of Maharashtra, commonly referred to as Konkan coast, which runs about for 720 kilometers and then can be divided as North Konkan, Central Konkan, and the South Konkan, each having its own peculiar physiographic setup. Now, before going for the physiographic, very brief physiographic setup of all these 3 regions, I'd like to mention over here that there are 3 level streams or rivers which are observed to drain into the Arabian Sea along this western coast of Maharashtra. These are the first level streams or the river are the major rivers which drain, which have their origin in the western Ghats or the scarps, and they run on the steeper slopes to drain themselves into the Arabian Sea. We have second level streams, those have the origin at the mid-level plateaus. And then we have the third level streams, which we call as the coastal streams, which originates very close to the coast and originates at an elevation of around 150 to 200 meters of elevation. And these are the coastal streams which we will be talking about, the portion of the mouth portion of these streams where we find maximum variations observed, and the models that I'm going to present over here are related to these coastal stream mouths. Now, the North Konkan region, as we can see, has a wide open flat plains with a few residual hills. And this is also reflected basically in the coastal zone in the form of wide openings of the major rivers. So there are some major rivers in the northern part. They are not as major as what we find on the eastern coast though. And these are like Vaitarna, Kundalika, and there are a few more like Ulhas and Dharamtar. Apart from this, we can also see the coastal streams over here, which I have highlighted with the elongated circles over here, which are basically the mouths of the coastal streams. The central Konkan coast comparatively appears to have very moderate sediment discharges. The spurs over here in this case extends right up to the coast and they form the headlands. And between the 2 headlands, we observe that there are different portions of deposition dominated coast that basically provide the anchorage point for the development of the beach barrier or the spit elongation. When we come to the southern portion of the Konkan, now this as against the coast in the north and the central, they are broadly dominated by the lateritic terrain. As compared to the central Konkan coast and the northern Konkan coast, the sediment discharges in these areas are comparatively of lower order, and the lateritic caps of plateaus at different levels, including the one which can be considered as littoral terraces, also have the capping in the form of secondary laterites. As a result of this, what happens is that most of the coastal streams have very narrow mouth, and the thalwic slopes in their lower reaches are steeper than their counterparts in the northern and the central Konkan coast. Once we get familiar with this particular physiographic setup of north, central, and the southern Konkan coast, there are some striking similarities or some observations which can be set up in this manner. The most striking amongst them is the existence of shore parallel segment of tidal channel in their lower reaches before they breach the barrier beaches. Then the high sinuosity of such channel, which is also observed, is quite suggestive of decreasing energy conditions, as well as the effect of tidal influxes influencing the overall gradient of the coastal stream and in its beaches. Most of the barrier beaches, those are observed over here, are more or less in the form of spit extensions in the north-south directions, with their anchorage firmly associated with the one of the headland. In most of the cases, what we observed was that most of the spits are getting their anchorages in the northern side of the northern headland. But of course, there are certain situations where the spit also has its anchorage in the southern headland. Besides these factors mentioned above, there are also occurrences of beach rock, which is running parallel to the beaches, and their generations are also observed, which suggests the possibility of the migration of many of these channels. Now, depending upon these local level studies and observations, 4 conceptual models are framed over here. The first model refers to the speed extension, channel elongation, and inlet migration. Now, in this model, it proposes the mechanism of speed elongation, how the speed elongates when the ebb channel is running parallel to the beach axis. In the first step, as we can see over here, the first stage is of initiation stage. The speed elongation has initiated and it is becoming parallel to the beach axis. The material that is scarred from the lengthening of the channel is the dominant source for the speed accretion, perhaps deposited at channel margin bar, which later becomes subaerial. Now, this lengthening of speed causes the parallel ebb channel to further elongate, which in turn further lengthens the speed. Inlet further migrates downwards, and as it migrates downward, the older inlet or the earlier position of the inlet starts filling in. Shoaling and subsequent closure of the inlet might again occur at the new location due to a simple reason, that is due to the elongated nature of the stream channel. It loses its energy, and more often, lot of sediment which has bypassed the inlet over there starts getting into the channel thalweg, and mostly the inlet throat gets constricted, and finally there is a shifting of the inlet towards a new location. Now, one of the examples cited over here for this particular model is from the central coast. Here we are having the Varavati tidal channel, which has consistently exhibited the process of channel speed elongation as the channel runs almost parallel, though in a sinus way, to the coast. There are instances of inlet migration over here as and when the earlier inlets experience sediment infilling. However, in the recent period, what we have observed over here is that the movement of the inlet is more towards the south rather than the north. Accumulation of the sand on one side of the erosion and erosion on the other side is very common. So this is one of the situations where the tidal inlet has migrated by breaching the otherwise continuous speed over here. Coming to the second model, this model refers to as speed platform breaching. Now, in this case, what we can see is that these also occurs at migrating inlets. But in this case, we have the main channel, which is again running parallel to the speed over here. The updrift barrier is where we have the speed formation, and it is fronted by the large intertidal platform. Large quantities of sand are bypassed when a new channel is breached. So there is all possibility that in this particular, due to its elongated nature of the channel will breach the speed platform somewhere here, as it is seen in the second diagram. And the major channel in the barrier, which is there, it usually runs parallel to the rear of the speed as it nears the inlet, and then it curves out into the around the speed platform. Speed accretion and downdrift extension of the barrier continues as the channel moves towards the new location. And the older location where the inlet was there, we have the portions of the inlet which have started infilling. Not only that, the lateral bars and the swash bars which were there of the older channel, they start appending themselves to the shore. So the former ebb delta in this particular condition, the sediments from the former ebb delta in this condition gets transported on shore to the downdrift beach as the flow is basically diverted. The example I'm citing over here is from the South Konkan. This is Guhagar coast, and it runs somewhere around 6.5 kilometers. At both the end, northern as well as the southern end, we observed that there are these coastal streams which drain out into the ocean. But as they are doing so, there are shore parallel channels which run over here, as we can see here in the north of Guhagar and south of Guhagar. So if you look at the south of Guhagar, what we have here in 2002 is a large intertidal speed platform, and the inlet is located due south of the South Guhagar location. By 2013, it is observed that this spit platform has totally obliterated. It has got breached towards the relatively towards the northern portion. And by today, that is by around 2021 or 2022, we can see that the channel, which was otherwise terminating into the sea at a lower location, has migrated much up and is running parallel, forming two parallel spits, one towards the landward side and one towards the seaward side. And it is having the inlet in the northern direction. But however, again, in the present day, when we visited, this breaching of the tidal platform, of the spit platform has occurred. And there was a lot of shoaling that was going on over here. A lot of sediments were trapped in this particular region, suggesting that this will finally close and the remnant part of the tidal platform over here will finally get appended to this secondary bar, which we are observing over here. More or less similar situation was also observed in towards the north of Guhagar. So again, spit was, the platform was breached over here, and we have the elongation of the channel. And finally, today again, the channel has shifted, migrated towards the south. So in this model, we are concentrating more on the formation of the tidal spit platform and how it breaches and how it causes the movement of the sediments over there. The third model is referred to as ebb tidal delta breaching. Now, at some inlets, the position of the throat remains constant or stable, but the main ebb channel migrates over the ebb delta. Now, this pattern is sometimes seen at inlets which are naturally anchored by the rocky shores, anchored by rocks and rocky shores on either side, on one side. And they are also observed where we have the stabilized inlet in the form of jetties construction. Now, here what we can see is that the ebb channel, which is there, it migrates cyclically downtrip. So there is a movement over here which can be thought of as a cyclical movement. So as the channel migrates with the dominant direction towards following the dominant direction of the longshore transport, it produces a preferential accumulation of sediment on the updrift side. Further, we have the deflection of the main ebb channel. So this main ebb channel, it keeps on deflecting, deviating from its more straighter path, due to which the severe deflection of the main channel, it will produce hydraulically inefficient flow at the inlet. And this will induce the ebb discharge, which will get diverted and takes a totally new and more straighter path towards the sea. Whenever this happens, the abandoned channel starts filling with the sediment deposited by the tidal and wave-generated currents, and the breaching process commonly results in the bypassing of a large portion of the delta sand. This is the example. This is the same area which I have referred in the first model, but in that model, we are referring to the portion somewhere in the western side. This is the tidal inlet throat, and the front portion is the beautiful ebb delta that is exposed during the lowest low tide. And here we can see this is a stabilized inlet, and as the channel takes more longer path to curve out into the sea, it loses its energy and it will take a more straighter path over here to drain itself out. And then the remnant of the bars will get welded themselves to the landward portion. The last model over here represents the flood delta formation and bay filling. As the tidal bypassing will occur, sediment will enter the inlet on the flood tide. Being wave-dominated coast, in this case, flood tide dominates the sea. Ebb is weak, and as such, influx of the sediments during the flood tide will be very high. And scarring and withdrawal of material out of the bay during the ebb tidal will be very, very low or negligible. Now, due to this incoming sediments which are getting bypassed along the drift towards the bay side, deposition of the material will lead to the formation of the flood delta. And in cases, if the sediments keep on depositing during the dominant flood tide conditions, then you might have a very peculiar condition where the proper flood delta with all its different components are visible will be found over there. Like you might have the flood channels or the flood ram, the ebb shield at the behind, and the swash bars, the ebb spits, and also the spillover lobes will be visible. Now, stabilization of the flood delta might result in establishing the salt marshes. Now, these salt marsh grasses might cause the land to be built further above the high tide level, and then we can have a new land emerging over here in the form of island. Now, this flood channel might start deflecting eventually if the amount of incoming sediments are not that strong. And this deflection will be due to, as I said, excessive growth of the flood delta, leading to the migration of the channel. Now, even though the inlet, in some cases, we'll find that the flood delta inlet remains stable, but whenever we have the migration of the inlet in those specific cases, like in this particular case, the 4th diagram, the main channel as well as the inlet will migrate, and this migration can be in downdrift or the updrift situation, depending upon the local conditions and the sediments those are bypassing in over here. This is the example of flood delta formation from the southernmost part of the central Konkan coast. We are having, this area is the Srivardhan Bay, and this is the flood delta which is formed over here. This is a tidal inlet that we can see. I'm showing the lower image. And all the different components of flood delta are visible, like we have the flood ramp, the flood shield, and even a small area zone which is lying much above the high tide line is visible over here, which has formed an island. Now this flood delta formation in this case is having a stabilized tidal inlet, and this inlet doesn't have not shown any migration towards the north. I'm saying north because south we are encountering the rocky headland. So this inlet is quite stable, and thus in the photograph upward we can see the frontal portion of the speed bar over here, a very huge platform which is being backed by the flood channels, and then beyond that we have the flood delta. So in all, we have seen here 4 different models which are being representing the sediment bypassing at the inlets along the Konkan coast. And these occurs through a range of processes that have been identified over here in these 4 models of natural inlets. All these inlets that I'm talking about are of natural origin. By this, what I mean is that there are no jetty constructions. There is no human interventions in terms of maintaining the stability of the inlet. Similar models, of course, can be generated for jettied inlets, but the situation will be quite different. And all along the Konkan coast of Maharashtra, we only have one instance where we have the jetty inlet. Otherwise, all the inlets of these coastal streams are in their natural setup. A commonality of all the unstructured natural inlets is that sand bypassing ultimately will result in the formation of landward migration and attachment of large bars to the downdrift shoreline. Now, the amount of sediment content in these bars varies somewhere between 20,000 to 100,000 cubic meters. Specific study that was carried over a Valoti, it was observed that the sediment content in the bars varies between 17,000 to 40,000 cubic meter. Bar welding is a repetitive process which was also observed in all the situations, in all the cases, which represent each and every individual model. However, further process can be done for them, like if this bar welding is a repetitive process, then we can go in for frequency analysis of this bar welding. And the actual sediment volume and the frequency of the bar welding will definitely depend on the inlet size, tidal delta morphology, rate at which sediment is delivered to the inlet, and the type of bypassing mechanism. But in short, to summarize my work, I can say that these are the 4 models which I'm presenting over here, which more or less are applicable to all natural inlets along the Konkan coast of Maharashtra. Thank you.